All right, welcome into this little tutorial on how to run and operate kind of Workbench specifically for Fluent. So this is a fluid solver provided by ANSYS. I use Workbench to kind of organize all my different tasks, model making, flow making, and all that fun stuff, meshing, and of course actually solving my simulations. So this is going to be a little tutorial for that. Sorry, stumbling all over my words already. But let's kind of get into it. You'll see it's actually already open down here. I just have kind of a little reference file for myself. If you ever see my mouse go off screen like this, that just means I'm pulling something, checking my recording, checking my reference, or I got some files I need to open. So I'm going to start by actually opening the program, pulling up my applications. So I just clicked on my applications folder. This steps if you're using Santa Clara's remote desktop system. It'll be here, but if you're not using that system and found this video for your own research, for your own classwork, whatever reason, own personal work, some of this, wherever you have ANSYS installed, you'll want to find. But for those on the ECC, opened up my applications folder, and I'm going to go into my EE, electrical engineers are actually the ones with it. I'm looking for this ANSYS 2023 R2, and I'm scrolling down to the bottom for Workbench. Now, as that opens, I'll give you a brief little spiel about Workbench. What its main purpose is to organize workflows for ANSYS. So as you see, it opens up. ANSYS has a whole bunch of different products that you can use, so you can solve thermal problems, structures problems, electrical problems, basically anything you can think of. I don't even know necessarily what some of these couple field parts are, but you have buckling problems, anything you can think of, they have options for you. And they've organized this in a couple ways that I know of. Some of these lower ones I have yet to play with. So if you're interested in those, you can look at it yourself, right? Optimization, robustness, some different options for you down here. But again, as I said, I'm looking to solve a fluids problem, specifically using Fluent. You'll see that there's two different options for Fluent, one with Fluent meshing and one without. I use this one without Fluent meshing. So I click on it, I drag it over, and I create a standalone system. As you can see, it pre-populates all the things that are needed for this system. So in this analysis systems box, it'll come up with these folders with all the different parts. You then can also build your own custom one using this component system. So I could pull out my mesh that I want to use, a geometry tab, and you can kind of build your own system. But I much prefer these built-in systems that they already have. Before I start actually using any of these, quick little tutorial for some of the Workbench things. The real thing you need to know is kind of your saves are up here. I don't necessarily, this I believe is like their cloud saving program. I'd suggest just saving to your desktop, which is these bottom ones. And then you have your classic file, view, tools, units, all that things, all those good things. If I'm assuming you're working in metric, so you're going to want to go ahead and flip that to your preferred. I use the metric system myself, but if you use other ones, this is out where you can change that. Without further ado, I'm going to actually get into making my geometry and starting up my system. So by default, I just right-clicked on geometry. It usually makes this discovery geometry is its default modeler. What I used is DesignModeler. It's just something I'm more familiar with and learned on how to do this with. So that's what I'm gonna. So I right click on the geometry, and then I'm gonna go ahead and select my new DesignModeler geometry. That's gonna take a little bit to pull up. You can see if I go back to my workbench, down here where it says double click component, you might have noticed that move to opening whatever program you want. So if you're expecting it to be working on something, you can often see what it's working on down here. So I'm just minimizing that so we can start on our modeler. One of the things I'm expecting is I actually already made my models out in SolidWorks. It's the CAD software I'm most familiar with. So I'm gonna go ahead and import one of those models. To do that, going over to File and File, Import External Geometry File. You can, if you used an ANSYS software CAD file, you can do this attach active CAD geometry. But yes, I used SolidWorks for mine, so I'm going to want to import an external geometry file. Now, where did I save that again? Yeah, so I'm just going to do this Onera M6. This was just one of the files on my desktop that had all my different wing geometries. I highly suggest using this parasital file, which is this .x_t file. So I'm going to actually come here and select that specifically. If you look down here, all the different options to import, they have added this SolidWorks import, which might actually work better than what I'm doing, but the program I learnt on, or the version I learnt on, didn't yet have this feature, so that's why I use this parasital. It's been the best in practice for me. I've tried like a classic STL file and a couple others, but they'd import with some kind of gaps or holes in their mesh. Or not in their mesh, but in their CAD file upon import. So that's why I use parasital. It's just worked the best and caused the least amount of errors for me. So I'm going to select that parasital file. Again, I've selected which model I want. So I'm going to open that up. As you can see, there's no real update on the screen. To get anything to happen, you'll see a lightning bolt next to it. You can either right click and generate, or there's this generate up here. You can click either one of those, so I'm gonna go ahead and generate. And now you can see it imports in that model I'm looking at. Couple notes for this import. Here you can see some of the details. You can clean the body, so in case you had kind of a rough geometry file, you can make it clean that file up more or less. You can refresh, and that'll just kind of cause it to recheck that file more often. And then you have a couple other options. I wanted to import it as a solid object. If you were interested in a surface only, you have that option as well. So since I want a solid, I want to check both my solid bodies and my surface bodies, not just one or the other. When I imported that, you'll see that now I have one part and one body, so that's my solid there of that imported geometry. So now that I got my wing in, we're interested in making kind of a pseudo wind tunnel. So now I'm going to start kind of sketching out my wind tunnel box for this program. It's a little, I'm going to say, funky when it comes to sketching. So to actually start a sketch, I need to define up here which plane I want to sketch in. I'm going to want to do the YZ or YX plane, so I'm looking at kind of my cross section this way. So it's already on Y or XY plane, pardon me. So I'm going to select that plane. You'll see it brings up my axes. it always imports your object with kind of, I believe, the origin of my SolidWorks file at the origin in this imported. I can't guarantee that. I've always made my model like this, so I don't know if that origin is correct. You might need to play around with that yourself. But to start a new sketch for my box, I'm going to come up here and click on New Sketch, and you'll see that Sketch 1's opened up. Going to click on that and then switch over to this Sketching tab by clicking on it. Going to give myself a little more space to zoom out. If you want to orient the camera quickly, I'm just using the middle mouse button to rotate, and then I can also click on this Z-axis to make it perpendicular to that view. Again, I'm making that wind tunnel box, so I'm going to select a rectangle. Going to click my first point and my second point. You'll see that it imports that rectangle. To add dimensions to it, going to have to click down to that Dimensions tab. General is used as almost kind of a smart dimensioning tab, so if I click on a couple things, it's going to try and figure out what I want to do. I'm not a huge fan of that just because there's some unknown that comes into that, so I prefer to define what I'm actually looking for. I'm going to start with some horizontal lengths. Clicking on my one line and control clicking my second line, and you can see that I have this arrowed line, which as I click again, it defines H1. You'll see that H1 populates down here, and I can modify that dimension. So for this, I believe I'm going to go for about 10 chords in front. 10 chords means 10 chord lengths. My wing is about 1 meter in its chord length, so I'm just going to do 10 meters. Oh, I wanted 10, my bad. Couldn't put the meters in. See what that size looks like. That might actually be a little bit big. I'm going to move that down for 5. If you're actually doing this for research, I would highly suggest kind of doing a sizing study where you try a larger and smaller box to make sure that your box is not influencing your flow behavior. But for now, as I'm more doing the tutorial, I don't want it to take forever to run, so I'm not doing necessarily as large of a box as I might think is necessary. Now that I got the space in front, I'm going to go for the space behind. So again, I still have horizontal, and I'm going to control click for my second line to get this second distance. This is the one I'm going to go ahead and do 10 meters. 10, my bad. What I'm noticing is if I put an M in after my measurement, it doesn't actually save it, so I have to do it afterwards. So now that I have my second part of my box, gonna switch down to vertical, select for the top. I'm also gonna do 5 meters, as well as the bottom. Again, just control clicking anytime I want to select more than one line. And there we have it. So that's going to be my boxes defined and constrained as I want it. Again, this box is probably a little small for this problem to get very accurate results. I'd say vertically it might be fine, but again, I generally push back this one to something more like 15, maybe even 20 for behind my wing, and maybe something between 5 and 10 for in front to give it the right amount of space. But again, for this tutorial, gonna keep the box a little smaller so simulations run faster. Now that I do have this sketch made though for my first box, I'm going to switch over to my modeling tab again, and then I'm going to go up to create, and I'm going to extrude this. Again, I'm going with that 5 meters, just making it kind of a nice consistent. If I rotate it, you can see it came out in my Z direction as positive. I actually want to flip that direction, so instead of normal, I'm going to go to reversed. There's also both asymmetric and symmetric. That would have whatever plane you sketch it on be the center plane in case of symmetric, or allow you to extrude two different lengths if you did asymmetric. But again, I'm going to just keep with reversed for this one. And then I'm wanting to add material, just using the normal direction to my sketch. Extent type fixed, 5 meters. It's not a thin surface. Merge topologies, I think, is fine, but I'm going to check that in a second. So now that I do that, now that I've edited these definitions, you'll see that there's this lightning bolt next to it. Again, I just have to click generate to make it. What I was looking for and making sure of is now I have two bodies here. One solid body that was, remember, as we imported it, we imported a frozen. That is important. And then one extruded body, which was extruded as add material. You'll see you could have also added frozen, but we will want our actual big box to be material, not frozen. Now, in addition to this larger box, I'm actually going back to my XY plane, and I'm going to make a second sketch. So again, I just clicked on this little new sketch button, and you can see a second sketch has appeared. Going to go back to my sketching tab. What this box is going to be used for is in our meshing, we're going to define a wake area that we want to be a finer mesh than the kind of far field mesh might be. So this secondary box is just to define that kind of more refined meshing area. So again, just moving over to rectangle, you might have seen that C appear. Anytime it's going to make something coincident, which means like on top of a pre-existing line, it'll have this C, just so you know that it's kind of auto-locking to that line. But we don't want that for now, so going to make this front kind of just free-floating, but I do want it to span the entire geometry of our box, so I do want it coincident with our back edge. Now going to go back to my dimensions tab, back to my horizontal, and control click to start putting in some distances. I'm only going to do 2 meters instead of the 5 meters. And then for my vertical, again, 2 meters and 2 meters is the sizes I'm going to go with. As I said when I was making the big box, you'll likely want these to be generally bigger for most of your models. But just for this sim, I'm keeping it a little on the smaller end for things to run faster. But now that that's all made out, gonna go back to my modeling, gonna again go to create an extrude, make sure my geometry is sketch 2, so gonna apply that. This time instead of all 5 meters, I'm only gonna go 2 meters. I think that's long enough. I'm gonna flip my direction from normal to reversed, and everything else should be good. The one change is instead of adding material, because this is not gonna be a physical box, it's only gonna be there for mesh refinement. I'm gonna come over here and I'm gonna add a frozen instead. So just a heads up with that, and then coming up and generating. So you can see my large box and my smaller box in both views. Now from here, I'm gonna actually, can I do that in this program? I believe so. I'm gonna go to view and I'm gonna flip it over to a wireframe. So again, you have a couple different options for how to view it. I switched from this shaded exterior and edges to just a wireframe so I could better examine these boxes. right? If I'm looking out through the back, I can see that my wing ends about here, and I still have some of this refinement area to go. You will need your kind of refinement box to extend past your wing so that you don't lose the tip behavior that might be going on with that. But yes, now that I have my boxes made, I can start kind of playing around with my wing itself. So one of the things you want to think about as you use Workbench is I'm going to be copying the entire system that I make for future systems. So whatever I make in this kind of first system, I want to make it in such a way that for later problems, it's set up well. So what I'm going to do for this system specifically is I'm going to add my rotation of my wing into this first one. Even if I were to simulate this at 0 degrees, I'd still want to add this rotation so that when I copy and paste the geometry into future problems, I can change those parts. So to add a rotation into this, I'm going to go over to Tools, Create. My bad. I'm going back to Create, and I'm going Body Transformations, and I have this handy dandy little rotate feature. So I'm going to click that, and you can see that it rotates, adds a boy here. Now, when I want to select my body, I can either select it in my designer, or I can select a body from here. I'm going to actually do it from here. I find it slightly easier, and I'm going to say Apply. I'm not going to want to preserve my bodies. If I did preserve my bodies, then it would have 2 wings, one before rotation, one after rotation. We don't want that. For my axes selection, I'll want it in this Z axis to rotate about my Z. To get that Z axis to display, I'm going to go ahead and click this ZX plane, and now you can see that Z axis is displayed. Going to click on my axis selection, and then that line we just showed. Now, to check my rotation, I'm going to leave it at 45 because that's pretty easy to see, but I'm going to hit Generate to actually rotate it. What you see is I rotated up. I did not want to rotate up. I wanted to rotate the other way for an angle of attack. So I'm going to go back here, right-click on Rotate 1, and go Edit Selections. And what I'm simply going to do is the body stays the same, going back to my axis selection, and if you notice this little red arrow, just flip it to the other one. And then now I can hit Apply and Generate. And you can see now it's 45 degrees in the direction I'm wanting. Obviously for a wing, 45 degrees is rather extreme. I'm going to actually, for this first one, leave it at 0. Because my first angle that I look at is 0 degrees. But the reason I did put this rotate in this early is because it's going to help me in the future make more of these, and I can just kind of copy this entire geometry into the next system. So now that I got kind of my wing able to rotate, my box is set up, the last thing I'm going to do is go back to my Create, and this time I'm going to make a Boolean. For this Boolean, I am going to not unite. That would be adding 2 things together. I'm actually going to subtract. My target body is what I'm subtracting something from, which is going to be my one actual material body. And my tool body is actually going to be my wing that I made. So again, target body, I'm going to click on my solid and apply that. And then my tool body is going to be my wing that I imported and apply. I'm not going to want to preserve the tool body. I want that to go away. So now when I hit Generate, you see I've moved down from 3 bodies to only 2 bodies. That's because I've combined my solid large box with my wing. Now, in this wireframe, you might not really see what's going on. So what I'm going to do is I'm going to go back to my view and switch back to my shaded. And what you'll actually see if I go ahead and zoom in is now we have this wing body cut out of my solid body. So it's pretty rough looking in this preview. I think that's more to do with the how it previews this versus the actual kind of geometry that it'll send down the line, but we can easily check that in our next step. So this is all just how you kind of make your domain set up what my wind tunnel box would be. I've set up this secondary smaller box for mesh refinement. I subtract my desired object from this large body, and I'm ready to move on. Since I am ready to move on, I'm going to come up here, not export, but just going to hit save. Doesn't hurt. I never actually saved this project yet, so I'm just going to go out to my desktop. I'm going to go good old example, because that's what I'm making it for. And I'm going to save that file real quick. And as you can see, everything's nice and saved. I have this checkbox next to my geometry, so I'm good to close out my geometry tab. And now what's nice about Workbench and why we use it is now that I've made my geometry, it can be flown right into our meshing program. So I'm just going to double click this mesh to open it. You can see it's starting my mesh. Just have to wait a little bit and it'll pull up the meshing program. Just waiting for everything to load up. It can be rather slow, but as you can see, it's all kind of imported my geometry already for me. I can go into this geometry. I see my solid of the wind tunnel with the wing cutout and a solid of my refinement box. So that's perfect. And then I have my meshing tab here. It comes with some defaults already done. I don't actually use I haven't used many of these kind of options up in the box. So you're free to look at those, but just realize most of the things you can do can be done by right-clicking down here, doing different things that you might want. So if I want to do sizing, I can do it here or up here. I'm going to use more this right-click method just because it's what I'm more familiar with and what I prefer to use, but you can also find them up here. So to start, I'm actually going to show you what its default mesh is like. So I just went ahead, click generate, and this is what it makes by default. So you can see it kind of refines it around curvature. Here you can see a better curved wing for us. Yeah, refines our mesh around the curve. Let me hide that body. So I'm hiding my refinement one just so I can see just what it's actually meshing my wing about. I don't necessarily need to see what it's meshing that refinement body because it's not really used. It's only used for mesh refinement. So now that I have kind of the default, I'm going to want to go ahead and refine some different things. First, this is not an acceptable mesh size for my wing's surface. So I'm going to want to start by actually defining my wing. To do that, I'm first going to change it to select my faces. So it has this smart select where it'll try and select what it thinks you need, but I much prefer defining what I actually want to select. And for this, I'm only going to be selecting faces. So what I'm doing is I'm just clicking down my wing into kind of that base. I'm going to right click it and actually make a create named section. This is going to be called my wing because that is what it is. You'll see your named section comes up here. If I go ahead and expand that, you can see, again, it makes a relatively rough kind of preview for you, but when it actually makes the mesh, it's much better defined. Now, I want all the surfaces of my wing to be selected, so I'm going to select this other face, and I can just click Add. Select a face, click Add. Select a face, click Add. Add. And I can kind of rotate round, make sure it's got everyone. Probably doesn't have this back edge, so I'm going to add that guy as well. So that's how I select my faces. Another option you have is to select one and use this extend, and then you can use extend to limits. In this case, it kind of got all my faces, I believe, but my end. So green selected faces, that might still be red. So sometimes that kind of extend limits works, but you'll still probably have to add some of the other faces on your own. Before I move on to making my mesh, I'm going to go ahead and name the rest of my faces real quick. So click on this first one, right click it, and then create a name selection. This is my inlet, if I can spell. Then I'm going to have my outlet. Going to have my close wall. Far wall. Top. And last but not least, my bottom. So now that I got those, sorry, I just had to double check I was still recording. Now that I've named all those walls, I can start changing my mesh. The first thing I'm going to add is something just called sizing. So this will define kind of the size of node I might want at different places. For my geometry, I'm going to go ahead, right click on my wing and select items in groups. That'll select all my wing faces. And then if I go back to my sizing, I can come here and apply that. So now I have all 6 faces applied. I'm going to define an element size. You have a couple different options. I'll show some of the others later. Will I show some of these? I might actually not show any of these others. But I'm going to change the element size to start. Its default is 0.9. That is much too big. I want something around 100th of the chord. So I'm going to go 0.001. I think that's 100th. That sounds like 100th. 10 to the negative 3. You'll see it makes the defeature size on its own. I'm perfectly fine with that. Usually the default works well. If you're finding the mesh might be having some problems, that's when you might want to go ahead and come into this defeature size and actually decrease it or increase it. I believe you want to decrease it so it'll go even more refined in the places that it might need it. But you'll also want to kind of mess with your local min size, and that can just help with some of the errors that you might encounter in your meshing. So again, that's your local min size and defeature size can help solve some of those meshing problems. So now that I've made that, I'm going to actually go ahead and generate my mesh again so you can see what happens because of that. You'll see it makes the old mesh this kind of pink color as it's going. Shows you the progress down here. Can actually click on that and it'll pull up this little window to let you know how far along it is. Yeah, I might have made that a little smaller than I was supposed to, so we'll see how long this takes. What it really loves to do is kind of freeze and then jump forward or jump back, but let's hope that doesn't happen too much and that it actually solves it. I might actually just cut this section. Yeah, so this is taking much longer than I want for this kind of tutorial, so I'm going to go ahead and stop. You'll see it's a failed mesh because I stopped it myself. I may have given this one too many zeros, so I'm going to try it with this different size, and let's try this again. Does it like me more now? Hopefully. Yeah, already out to 3, 4. Perfect. So now that my mesh is finishing up, yeah, I think I added one too many zeros. You can kind of zoom in and see your size. Again, I might say for an actual simulation, I probably would go for something like 0.005, so about half the size you're currently seeing. But for this tutorial purposes, that should be more than fine to give a nice gist of what you're doing. My next type of sizing that I'm going to add in is going to be what's called an inflation. And this is going to really help you capture boundary layers right close to the surface. Again, this will be on my wings, so I'm going to right-click on wings, select those items in group, go back to my inflation, and apply that geometry. Pardon me, I believe I got that wrong. Did I get that wrong? Yes, the wing that I selected, so select items in group, that wing shouldn't be the geometry, it should be the boundary. Pardon me, I can't apply that yet because it's selected twice. So actually, my geometry, I'm going to go over to select body, and I want the entire body to be my geometry. And then my boundary is when I come here to wing, select items in my group, go back to my inflation, and that is my boundary. I'm going to have about 20 layers. 20 layers makes sense. And I'm going to go 0.01. So same amount of, same thickness as my desired cell size at that surface. That's on me. I generally don't use smooth transition. I'm going to use total thickness. So there's a couple different options here. Total thickness talks about the thickness of all of your inflation layers. First layer thickness is just what, as it says, that first layer is. Smooth transition will transition between inflation layer and whatever mesh is surrounding it. And then these aspect ratios, I'm not exactly sure how it defines aspect ratio, but again, I use this total thickness myself. And this is where I want to go 0.01. So now right up against the body, it's going to be really small layers, which again helps capture that boundary very well. This growth rate talks about how much larger the next cell, the next cell is compared to the previous one. So if I have an growth rate of like 1, they're all going to be the same size. If I have a growth rate of like 1.5, each cell will be 1.5 times thicker than the previous one. I believe the default's 1.2, and it works relatively well in most cases. So I'm going to go ahead and generate my mesh again so you can see the impact that this has. You'll see here, just to monitor the progress, if it really gets stuck on anyone in particular, it might be a sign that it crashes. Perfect, so that mesh should be finishing up here shortly. I'm seeing 100%. Please don't give me an error. If it does, I'd be sad. I am not sad. Let's go. So here we have that mesh, and here, if I zoom in quite a bit, you can see those inflation layers. So each layer gets slowly thicker and thicker, and it's real nice and thin right at that surface, which makes it really good at capturing kind of that transition between what's happening on the surface versus the actual flow itself. What you can sometimes notice, and what it sometimes does, is it might have some interesting behavior out the back, especially near that trailing edge. So if I go into my inflation, right, as you can see, this is just a cutoff edge. If you end in a point, it usually has more problems than if you end in a flat surface. But if it's really giving you problems out here at the end, you may actually want to go back to your face sizing and play with some of these definitions again, and that can sometimes help the inflation layer better capture your trailing edge. And if I slide over to my leading edge, because usually that curve is important, you'll see it's relatively it's rather bumpy in this model. So if this was for actual research, I'd probably go out back to my face sizing and refine this again, maybe half the size of the cells, maybe further if I felt that was necessary. But now that we've gotten our inflation layer, the last thing I want to do is to insert one last type, and it's going to be another sizing type. This time, instead of a element size, I believe I want to go a body of influence. For my geometry, I'm going to select my entire body, click apply, and for my body of influence, I'm going to come up to my solid here. I'm going to show that body again. I'm going to want to click it, and since it's hid behind something, you can see that since I have two bodies, I get two options here. I'm going to not want my big box, but my small box. So I'll click the second plane, go back to my body sizing, and select apply. So now I'm using this smaller box to change that geometry of or change the meshing in the area of that smaller box. I can hide that again, hide that body, go back to my body sizing. I don't want the default. I want something like 0.1. So in this kind of box, I'm going about 1/10 of the chord. Again, I might suggest more like 1/5 of the chord length for actual research purposes, but for this one, it's relatively fine at 1/10. And I'm actually going to switch my growth rate down to 1.1 from the default, so it increases in size a little slower. And let's go ahead and generate that mesh. This will likely start taking a little longer as I've increased how many cells I'm actually making. So just be prepared that it might take a little bit to run. Not too concerning, but a heads up for you in case you're a little uneasy. I'm probably going to cut here, and then you'll see me again when it's meshed. Alright, so it looks like my mesh is nearly done. It's just kind of applying it, making that visual pop up for me. I can see it's at 100% now. And there we go. So if I click my mesh now, you can see how it turned out. I'm actually quite happy with this mesh. So you can see near the surface, we start with nice small cells. We get to this kind of slightly larger celled trailing edge, so it captures that wake pretty well before getting out to these largest cells out at the edge. A couple tips and tricks as you go for larger meshes, if you have a larger box or whatnot. My first tip would be you can probably change these element sizes at the farthest and probably actually increase that size. So if I go into this mesh and actually change the defaults here and like the sizing out here, so maybe I increase this max size to kind of 2 or 3. If I had a larger box, I'd probably increase that. With the size of box I have now, this is pretty damn good actually. But yes, if you want to change kind of this last layer of cells, you can just go into this mesh in general and play with some of these numbers. Trying to look if there's any kind of tips I have for you. Not necessarily. You can check your quality here. If you make kind of my target skewness higher or lower. I believe lower is bad. I could smooth out my model more or less. So if you have kind of a jagged model and you want it jagged, you might not smooth as much. That's going to try and kind of capture curvature better. So if I'm expecting a curve, I might smooth it more. The inflation, we made a custom inflation because we just wanted around the wing. If I wanted an inflation around every edge, you can change that, but that's quite intensive and quite unnecessary. There's some advanced for like how you call your computer stuff. I'm not huge on actually like how computers work. I just use them. So you'd have to look into that yourself. The last one that's kind of important for us is our statistics. So this mesh has about 3 million cells, if I read that right. Yeah, just shy of 3 million cells, or elements as they call them. I think for my actual study, I have more like 5 million, if I remember off top correct. So it's not bad, but again, I'm probably about 2 million cells short of probably a good mesh. But yeah, so that should have saved and figured out our mesh to a standard we like. I'm going to come up here, save my project. That'll take a little bit to save, but hopefully not too long. Now that you see it saved, I'm going to go ahead and close the window. Now, a difference you'll notice when we closed the window for our geometry, it already had the check. Unfortunately, it does not save your mesh results when you have the meshing software open. You'll have to run it outside. So to do that, I just right-click on mesh and I click update. You'll see this turn red. You may not actually have this progress bar when you start. If not, it's just going to be in this show progress, and it pulls up what it's doing for you. So if you don't have this kind of bottom one, I highly suggest coming down here. It'll say show progress and pull up that bar for you. But we just have to wait for our mesh to remesh and actually save to the workbench instead of just in the file itself. So I'll see you again once that's nice and finished. Alright, so now that that has finished meshing, you can see it's moved to a check and my setup gets this little kind of, I don't know, circle-y arrow looking like thing. So I'm going to double click on my setup. Because we selected our Fluent fluid flow model, it's going to ask me how I want to set up my Fluent launcher. I'm going to want this to be double precision, and I believe I'm going to run this at, let's go 6 cores. Let me actually double check that. Task Manager. So just to show you what I'm looking at, right, we have our things running, performance, CPU. I have 8 cores. So I'm going to go ahead and let's run this at 7 cores. The reason if you were to actually do this, I'd suggest use all 8 cores, but I want 1 core for my recording software to be available, so that's why I'm only going 7. I do want double precision. That should be all you need. There's some other options if you have kind of a more advanced computer setup that you can play with parallel remote settings or whatnot, but at least at Santa Clara's ECC, we're just going to use kind of the defaults. Yes, my name's Andrew Mahler. I don't know if I introduced myself at the start of the video. Some of you might already know me, but we can see it saying starting Fluent, so we're just waiting for it to pull that up. Hopefully it pulls up on the right screen. It does not. Let me drag that over for you so you can also see it. It's a little large of a window, so I'm just going to try making it a little smaller. We can see it's trying to load everything. We can see a little console making all our stuff. Right now it's reading that mesh that we have and importing that into Fluent. Now that everything's in, I can go ahead and click OK. My bad. It wasn't fully loaded yet. Now I can click OK. So now we have our model all loaded up. It's semi-smart, knows what my inlet and outlet might be, but I'm going to have to define and double check a bunch of different things on it. So let me see. So again, I'm not going to use many of the things up here. Lots of the things you see me doing can be done from one of these tabs up here. But I just find it easier to do in this tree down here rather than worry about those ones up here. So we're starting in this setup general. That's what's pulled up already. We have a couple different, these first mesh options, since we've already made the mesh, aren't too important. You can report your quality in case you're interested in that. But for the most part, you should be good to go. For my solver type, I do want a pressure-based. I want an absolute velocity formation, and I'm going to be doing a steady state. If gravity is something you're interested in, you can add gravity into your simulation. Probably more important if you're doing like water or something, but I'm going to be doing air, so that's not too worrisome. I just expanded my models, and then I'm going to double click it to pull it up. I still want it expanded though. Most of these defaults, I believe, are correct. I'm going to go ahead and click edit though. Going to expand this. Phases. Okay. Yes. So that was all good. Didn't need to change anything there. I like the viscous model. If you really want to change things, you can also, I suggest right-clicking what you're changing in here or double-clicking it. It just opened on the wrong tab, right? So I double-clicked my viscosity for my SST K omega, and I have a couple things that I can change. If you're like incredibly familiar with the equations and formulas, you can actually change the coefficients if you have a custom one. But yeah, for the most part, you can select what type of model you're using, K omega, K epsilon, some different transition SSTs, different options for you to look at is really what's going on here. Hopefully you know what viscous model you want to run at. I'm going to click OK. Don't have radiation, not worried about heat exchangers. I think most of the rest of this is unnecessary for me, so it's really just that viscous I'm looking at. For my materials, my fluid, I'm going to be doing air. If I want to change that, I can double click my fluid. Hello, double click. Oh. I want to double click my materials, pardon me, and then create and edit. As you can see, my solid is aluminum. That's perfectly fine for this case. Again, you saw in some of the models you could do radiation, acoustics, or structures as well. And then what solid I use would be important. Since I'm only interested in fluid flow, whatever that solid is does not matter. Cell zone conditions, I believe default works great for these. Just kind of double checking. Yep, you can see it's air. So yeah, that's all set up and good. Biggest kind of thing you actually have to do is your boundary conditions. So I'm going to double click on boundary conditions. And you can see all those name sections that we have come up here, as well as a couple extras like interior solid that it auto-populates. You can see it auto-populates that as an interior, which is exactly what we want it with. What I'm here to define is what all my walls and inlets and outlets are. So for my outlet, I'm going to use a pressure outlet. You can also use, you have a couple different options here. The other most common outlet type is going to be a mass flow outlet. But again, it's very dependent on what case. If you're using different cases, you can change out what you want, right? Outflow vent or an outflow outlet vent. But most common you see is actually this pressure outlet. So I'm going to leave that here. If you want to change the backflow turbulence or any of kind of the parameters, you can do so in this box. If you're wondering how I got there, you should be able to just click edit here and it brings that up for you. But my outlet, again, I want that pressure outlet. That's perfectly fine. However, I am going to change all these other ones. For my simulation, I'm going to be simulating what a wing would be like out on a plane. And therefore, instead of using a wall, I'm going to actually use far field. Pressure far field? I believe a pressure far field. Yes, I want that pressure far field. Gauge pressure is perfectly happy for 0. My flow is going to be at Mach 0.3. Cartesian coordinates work. My flow direction is that X. You can double check using this little guy here that your flow's in the correct direction. Default turbulence values are fine unless you're if you're worried about a special case, you can add something there. Maybe you're worried about information and maybe that has a higher turbulence than typical far field might have. But defaults are generally pretty applicable. And I'm going to apply that and then close that. And I'm going to do that for all my top wall, my far wall, and finally my bottom. Nope, that's a pressure outlet. My bad. Sorry about that. I want a far field. And again, 0.3. The last place I'm going to apply that is actually my inlet as well. So instead of an inlet velocity, I'm going to do a pressure far field. And I can define that as Mach 3. The reason I'm using this far field again is because I'm assuming more so the conditions of a plane out in the air. I would use more the defaults of that wall and velocity inlet if I was simulating wind tunnel results. So that wind tunnel actually has kind of walls, top, bottom, top, side, and bottom, rather than kind of a far field. But since I'm considering this as a wing out in the real world, that's why I'm using these far fields. So the last wall I have not actually defined is my close wall, and that's because I am using a symmetry boundary. So I can just come down here, click symmetry. You can see there's nothing to kind of mess with there, and I can click apply. What symmetry does is it enforces a mirror condition. So as you saw, I only imported half my wing rather than a full wing. And using that symmetry boundary, I can basically half the size of my simulation while considering an entire domain. So that's very helpful when making your simulation more manageable for your computers. But realize that a symmetry boundary, while pretty good, isn't entirely reflected in real life. So you can go through some of these. As you can see, all 4 of those walls I defined as a pressure far field are considered inlets. My internal was already defined. My outlet's that pressure outlet. And finally, I have that symmetry and a wall condition. I realize I didn't double check my wing. We do want your wing to be a wall. It's a solid surface, so a wall is great, but I'm going to go ahead and go edit definitions to double check. What I'm looking for here is standard roughness, perfectly fine. If you kind of know what material or are simulating a specific material in real life, you can change that here. We want a no slip condition, so I'm going to leave that here. You do have this specified shear, so in case you wanted an object that had, I don't know, a certain shear stress on its surface, let's say you're simulating an experiment where you already knew the shear stress, that can help make it a little more accurate. But we are going to want this no slip condition, and it's going to be a stationary wall because that we're considering kind of the wing moving through air by making the air move, not making the wing move. So I'm going to apply that, make sure that is all good. Shouldn't need to worry about a dynamic mesh interface. Or these auxiliary geometry definitions. Those should be all good. Reference frames also should be good. Same. We do need to change our reference values. So you can see my area, density's pre-populated from air, lengths, pressures, temperatures, all that fun stuff, and velocity. I actually will want to change some of these numbers, and to do that, I'm going to actually use a handy dandy little trick compute these from my inlet. That actually did not compute as I thought it would. Interesting. Okay, so I've done a lot of playing around. As you probably saw, I got a little stuck, and a couple things that I missed. I was just looking kind of back at my reference material. So first that I changed is if we go back to our models and double click on my energy, we need that energy equation on. So you're gonna go ahead and press OK for that. The second thing that I missed was to use these far fields, we needed to define air a little different than default. So the default leaves all of these as constants, but at Mach 0.3, we can't necessarily say that. We could have some changes, so we just need to switch this density out to an ideal gas, and then we can click create or change and create, and then we're good to close. So now that I've updated those, I should be able to slip back to my reference values, and let's try this one more time. I'm gonna compute from my inlet. There we go. That's what I was hoping to see. And you can see a couple different things have changed. First, this density switched out. We've gotten a new enthalpy. The length doesn't change, pressure doesn't, but now we also should have this temperature. And most importantly, I was looking for that velocity to change, which I was not seeing. The last thing you'll want to do is change your area. In this simulation, I'm going to be showing you how to have it generate your coefficient of lift and drag, and this reference value is what it uses to compute those. So if I just double check, what is my reference value? There it is. So for the wing I imported, it is 0.8390. 555. So that is important to put in as we have Fluent calculate our coefficient of lift and coefficient of drag for us. Just double checking my reference again to make sure I don't miss anything. Looking good. So now that we have that created, I'm gonna slip on down to my report definitions, and I double clicked it. I'm going to want a new report, and this is going to be a force report specifically for lift. I'll start with lift and then I'll do drag. So it should open something up like this. I'm going to change my name to co-lift. Are you going to give me any capitals? Nope. Okay, no capitals. Co-lift. It's already on lift coefficient. If you wanted total force, you can also flip it to that. My force vector is positive y, just looking back down here, and that is my positive y is my lifting direction, so that's perfect. In case you have your model kind of angled funky, you can change that here. For my lift coefficient, it's going to use those reference values that I just kind of double checked. To give me my kind of 1/2, I think it's 1/2 rho v squared is 1/2 rho v squared times a is the bottom of coefficient of lift. So that's why we need to define those. Down here, you'll see a couple different options. You can make a report file, report plot, print to console, and create output parameter. The biggest one I do suggest is we do want it to print out to our console, and I generally change this report plot or no, I do want this report plot to be 1. So it updates kind of every point that it's reporting. So that should be good. Oh, for zones, I just needed to select wing. Since it's the only kind of solid, it's the only option for me. But now I can click OK. And we can see if I press that plus, we get a coefficient of lift. And I'm going to do, since it's still open, going to do another new force report. This time I'm going for drag. Going to call this co_drag. Drag coefficient, now it's in that X direction, gonna give it a print to console, want a report plot, report file, that all looks good. Click on wing, go OK. So now we get those 2 coefficients are made. And we have these report plots of coefficient of drag and lift, and those should be plotted out for us to see how they're going, and we'll look at those a little later. I'm gonna move on down to my initialize. Can close this out now as well. Usually the default is out in hybrid. I am gonna move it over to a standard initialization, and once again go compute from my inlet. You can see it inputs my velocities, my turbulence, my dissipation rates, and my temperatures. So now every cell will have kind of start at that velocity. Just makes solving it a little quicker. There's no calculations that I need it, or calculation activities that I need it to do, but I'm gonna move down to run calculation, double click on that. And I'm gonna change a couple of these. Number of iterations is the first one I'm gonna change. This is gonna be your total number of iterations that it'll compute. I believe I want something like 500, should be more than plenty. I'm gonna have a profile updated every time, but I'm only gonna have it report it every 5 iterations. I just am trying not to get it to, I just don't need it to tell me every single number. So I'm increasing that to 5 for it. So I get just a little less information sent my way, makes it a little easier to read, but I do like my profile actually being updated every point. Just makes nice smooth curves for us. And I believe that's all. If you want to mess with Fluent results, you can do it down here. I'm not a huge fan of how Fluent displays scenes and whatnot, so we're going to actually use a different program for it in this simulation. So since I do have everything kind of set up now, I'm going to come up here and I'm going to hit synchronize workbench. What's it called again? Yeah, workbench. Synchronize workbench cell status. Gonna click that real quick. Click it again because it was a little faster than I was expecting it. And now it's taking a little longer, which is what I was expecting, though it's saying not responding. Okay. So that should now be synchronized with Workbench. If I pull my example back up, you can see my setup now has a check next to it, which is perfect. That's exactly what I'm looking for. And now I'm going to go ahead and close my Fluent. Do you want to quit? Yes, I do. So it's just writing out some output file, saving how it's made all its setup, so that when I run it in Workbench, it'll actually run properly. Oh, I saw a little error, but I'm going to assume that's okay. So now to run my simulation, I'm going to right-click on Solution and first go Show Solution Monitoring. We'll see the console outputs down here, and we'll see the plot up here. So I'm going to go back to my project now that I have my solution tab, back to my project, right-click on solution and click update. So now we should see updating solution. I'm going to click show progress real quick, and we can see it's loading my current solution and starting that up. Clicking over to A5 solution, we'll see that console. It's right now loading up that mesh and starting that simulation off. So we kind of just have a little game of waiting. I'm going to keep playing this video for now as we start to see these first couple iterations. Perfect, that's what I wanted to see. So we have a bunch of different, a bunch of things that we can now look at. So to start, you'll see that it expands out this branch with two different plots. One is my residuals, and one is my coefficient of lift and coefficient of drag plots. If I click on the different ones, you'll see this update. It hasn't done much calculating, so there's not much to see currently. It has just finished out its second point. This is why I have it show me every point on the plot, but I don't necessarily need the numbers for every point. It's just a bit redundant. So you can see it's kind of chugging along its solutions. I'll give you a couple tips now for what to look out for. The first thing I'm looking for, and I'm just expanding my window, hopefully making it a tad easier for you to see. I like these negative numbers. I almost never want to see a positive number in my residual plots. If I'm seeing a positive number in my residual plot, chances are something went wrong. Likely your mesh is causing an error. There might be a hole in your surface that you need to look for. Could be some bad meshing cells. That's almost always the culprit. The first time you set it up, it could also be your solution setup. So what solver you chose might have something messed up with it. And some of those might be your problems. So just a couple tips to look out for. Again, that's if it ever goes positive. I am expecting it to stay negative. I believe we did a good job setting it all up. So I'm not too worried on that case. Looking down at this kind of output here now, we'll see it displays a bunch of different kind of parameters. So we have what iteration it's on, all the different things it's plotting above in the residuals, but it also spits out my coefficient of lift and coefficient of drag. Those are these kind of last couple numbers, which are right, so this would be my coefficient of lift right now, and this would be my coefficient of drag right now. If you look at these last couple, it tries to give you an approximation of the time it'll take. I've never found these approximations to be like even ballpark good. So yeah, that's kind of unfortunate, but just a heads up that that time really means nothing to you. And then how many iterations are left. That is in this kind of main terminal. And again, we have the residuals plotting. If I slip over to my lift, we can see our lift being plotted. This is a symmetric airfoil that I'm simulating. So I'm expecting small numbers, hopefully something close to zero, right? We're 0.005. We seem to be kind of moving back up to zero. Might oscillate a little bit, but we'll check in on it closer to when it's finished. And finally for drag, we can see it kind of drops down, finds what it is. Most of this is kind of drag due to the surface of the wing. So I am expecting some drag, and you can kind of check your theory, look up what the drag coefficient of your airfoil is in this case. compare to other studies or other papers out there to kind of get a sense if you're in the ballpark. But right now, this is all running fine. No problems are coming up. So I'm going to stop talking for a while, let it run, and I'll meet you back either when it's done running or it's right about to be finished running. All right, guys, so I'm back. I've let it run for a little bit here, nothing too long for this setup. You could kind of keep letting it go out to its 500, or you could stop it early if you so choose, which I am going to show you how to do now. So as you can see in kind of my residuals, it's getting very flat. It's still kind of decreasing a little bit, but it's rather flat out here. If I go over to kind of my coefficient of lift, we can see very little change, both in the plot, but also as I look down at these numbers, it's kind of the fourth-ish decimal place that's been changing these past couple iterations, right? 7979 to 10 to the fourth. And if I go over to my drag, again, that's incredibly flat. And right, it's 8 ones for the past kind of 40, 50 iteration, or 9.8 ones. So it's more or less found a solution. Depending on your precision, you might want to let it go farther. You might cut it off early. I'm going to cut it off early for this example, though. So to do so, you're going to want to hit this little X, which is a stop, and it'll give you an option to either interrupt or abort. You're almost always going to want to interrupt it. If I abort it, not only does it kind of hard cancel the solution, it'll also throw out all the data it's already calculated. If I interrupt it, it'll continue its calculation till it finishes kind of the next iteration and then kind of safely exit out. So if you wanted to calculate more later, you can come back in and start that back up. So I much prefer interrupting. The only time I'd suggest aborting is if something goes wrong and the data is unusable, then you can abort. But for really any practical purposes, again, I suggest interrupting. As that is interrupting, it'll take just a little bit to do. We can see now it's finished up. So I can kind of grab my coefficient of lift and coefficient of drag from out here if I want to, and do things with that. Let me go back to my project. If you want to continue calculating, let's say I just had to interrupt it because I know I was going home for that day, I was grabbing food or something. If I right-click back on solution, I have this option to continue that calculation because we interrupted it. If we aborted, we wouldn't have that option and have to start from ground one. Again, I think this 100 iterations took me maybe 10, 15 minutes with these kind of simulations. So I might expect more an hour for this 500 sim or 500 step case. But yeah, just something to look out for. Before I get into the results, what I am going to do is go ahead and slide over my actual research. So this is one of the cases that I've already looked into, already researched, and I just want to go through a couple of the different things you might see in these residuals and some things to look out for. So this first is another zero case, and I actually didn't abort this one. The solution ended up converging. So how I believe Fluent has defined convergence is it looks at these residuals, and once everything is less than our -3 on this plot, it'll consider the solution converged. It is important, remember this is a log scale, so kind of once continuity popped below that -3 as our last point, it decided the solution was converged and ended it on its own. And you can see here, right, lift's barely changing, drag's barely changing. So it's basically found its steady state solution that it was looking for. Sometimes it's only take 60, right? I had a pretty well-defined mesh and well-initialized mesh for this case, so that helps it take less. Also, 0's a pretty simple one to calculate. If I look over, let's say at my 2 degrees, we can see, again, we had convergence, but it took till kind of 180 for this one to converge. And you can see kind of how convergence plays out in your lift and drag. Is you start with some of this variability, and then it finds kind of an answer that it likes, and it stays with that. So again, some of that variability and then finding what it likes. Another option you might have, if let's say I pop out to 36. So in this case, it never actually converged. You can see here's -3, and we still have both continuity and what's this? Our K term. I'm not exactly sure what the K term is. It should be in the manual if you're interested, but it's just another measure of consistency between iterations. So you can see what ends up happening is instead of converging, it starts to kind of have this semi-chaotic but kind of repeating behavior, right? We kind of have some of these same behaviors. One of the others might be better to show that. All of these rather chaotic. Yeah, all of these rather chaotic. But yes, if I look over at my lift, you can see we've kind of stayed within the same bounds for quite a while, right? So more or less from 175 out to 500, the upper and lower bounds of my solution for lift doesn't really change. So there's no real point in continuing the simulation past this point. It's found a solution, more or less. Same with drag, right? We see pretty small variations in them. So once you see that, that's kind of another form I accept as convergence, and it works out pretty well for me. The other option, which I'm showing you here in these residuals, is you might see a solution have this kind of dip down to incredibly small numbers for apparently no reason. But there actually is a reason for this. Occasionally, if I were to interrupt a solution and then start it back up, the first iteration it considers is the same as the last iteration it calculates. So instead of starting up with an actual new iteration, it's basically redisplays and reiterates this previous point, and that makes it this incredibly flat and low, right, 10 to the -16 values. So that's just a consequence of stopping the iteration and starting it up again. And then you can see, right, so that's the point I started it up at for my second round through, and then it goes right back to kind of what it was doing before in lift and drag. So just a heads up, if you do have to use that interrupt, you can have some of that behavior. So you won't want to interrupt it if it's too close to the end, right? You can see I still have about 175 iterations to go, which gives me plenty of data to kind of look at the trends out at the end. So yeah, just a couple kind of visuals for you to understand a couple different residual responses that I've seen and what might happen with those. So just wanted to give you a sense of what's going on and some different behaviors you might be expecting to see. So now our last step in this for this angle is to make the results. So I'm going to go ahead and double click on my results. It opens a program called CFD Post. It's actually quite fantastic in visualizing our flow. Just dragging that onto our screen for us to see it. So that has now all loaded up, and we can start playing around. Middle click helps you rotate it. So you can rotate it all fancy like that. Might be a little fast for you guys. If I control click, I can translate it around. So let's say I want to get in. So control, and that's control middle click. So your middle clicks do all your navigating. So yeah, middle click rotates, control middle click slides around, and then you can use your zoom wheel to zoom in on the subject. A couple other nifty things you can do for moving around this program. If I go to the bottom edge or the side edge, you can rotate in a particular axes. So this will only, or this will, to do this, instead of middle clicking, which lets me rotate in any axes, when I have that kind of different icon appear, right, so instead of just this kind of general rotate, I get that line with a rotate around it. That'll force it to stay in kind of in rotation plane. So even if I move left or right, it doesn't rotate, it only rotates up and down. And I can also do that in our other axes. So that's for your Y. Again, that's just kind of going to the edge of the screen to do that. Finally, if I go right near this little coordinate system, you'll get the icon of rotation without a line through it. So no dot, just kind of that rotating. And that helps you rotate kind of in a circle around the screen. So that's some of the navigation for seeing different views if you're interested. To reset to kind of the standard view, you can click this little blue dot, goes back to ISO, and that's the standard view. You can also click on any of these axes and it'll go perpendicular. You can also click on kind of right positive X is this way. I can also click negative X to look down into the flow. So just a couple of the things you can do that I wanted to point out. I'm going to now go ahead and play around with a couple of the visualization options I've used. I highly suggest kind of playing around with them yourself, finding what's best for your case, because what I use best for my case might not be good for whatever you're looking into. So to start, I'm going to go ahead and look at these solids. If I go ahead and click the white box next to any of these solids, it shows up as a solid color, right? So I clicked my bottom and now it's blue. If I clicked my inlet, that could be blue and whatnot. If I double click on them, they bring up their kind of information down here. So maybe I don't want this blue. I can cycle through a bunch of different colors here, or I can press these three dots to come out to a more fine-tuned way. You can put in the hex code down here. You can find it on the graph here. I can select some basic colors they have here, whatever you want. If you do change it here, you just have to go ahead and click apply, and then it shows up. So if you change something and it's not showing up, make sure you hit apply. I don't want to see the inlet for now, so I'm going to unselect that. What I am going to do is something with our wing. So I'm going to click the box. Now the wing is shown. I'm going to double click the wing. So now I have details of wing down here. And I'm going to go ahead and zoom in a little bit so we can see what's going on a little better. Right now, we've only been looking at constant colors. Good for kind of, I don't know, defining your outlet and inlet. But not great if I want to show a variable. And I can show a variable. So if instead of a constant, I just clicked on constant, I can move down to a variable, and now I can display a couple different things. I have a bunch of kind of what they assume are common things to display if I just click on pressure. Or I can see the entire list by pressing these 3 dots. Right, so I can have wall shear or a specific direction of wall shear, same with velocity or forces. These are all considered solution variables. I can have geometric variables. So if I didn't know how far I put something, I could display x's, and I'm just going to display that real quick. Right, so I have different x values, which is downstream. So you can see everything's pretty close to 0. It might be more valuable if I actually go y, because that has less of a range. That's still all pretty damn green. What I'm going to change then is, instead of going -5 to 5, which is our global variable, I can change it to a local one. And that'll only kind of define based on my surface. So now, instead of it defining based on this entire box's geometry, it only defines my location based on my wing, what I'm displaying. So as you can see, kind of the bottom's the top, and that's red. Or the top is red because that's the farthest away, vertical positively, and then we get blue on the bottom because that's the furthest away in the negative direction. You can also custom define it. So right, I had global, I had local, but I also have user specified, and I can change my mins and maxes as well. Y is not too important. For a wing, pressure is a very common one that you will see, so we can flip back to pressure. Gonna click on that, click OK, and click, instead of user specified, let's go local, and click apply. Let's see what this looks like. Gonna just click on ISO to get that ISO view back up. Scrolling in, doesn't look terrible. That's kind of what I'm expecting. I'm gonna flip it over to wall shears to see kind of what that looks like as well. You can kind of see wall shears a little streaky. And yeah, you can play around with any different variable you want to display. And that's some of your options to do so. After you play with those, you can also change your color scale from linear to logarithmic. I don't necessarily know why you'd want to do that. There might be some of these variables that I don't mess around with that it's beneficial for. You can also change it from smooth to banded. If I move over to the banded, instead of having kind of continuous colors, you can see it defines these kind of distinct bands of colors and gives me the range at which they fall into. So I'm going to leave it as smooth for now. Going to reapply that. In addition to being able to change kind of the variable for this, I can also change how it's rendered. So you have kind of transparency settings, shading settings. You can turn on or off lighting, right? So you can see the bottom wing, the bottom of the wing's pretty dark because lighting is on. If I uncheck that and apply, you can see it's all pretty bright now because it's not getting the shade from the top of the wing. So that can be definitely beneficial sometimes and not beneficial other times. It can give kind of a false impression of some of your colors, but it also gives kind of an idea of curvature. I usually don't see too much change with specular. Probably changes something, but I don't know what. So you can feel free to play with that yourself. You can also show the mesh on it, right? I have a pretty dense mesh, so it makes things a little hard to see, but could be a good way to check your mesh in case you're concerned something went wrong. You can show that as well. I'd avoid applying any textures, right? This is a metal texture. It kind of makes it dark and shiny. But for the most part, I probably avoid those. There might be use cases for it, but I just don't know what those are. The other thing you can do is kind of move around where this is displaying. So if I move over to my View tab, I can rotate that display, translate it, scale it up or down, reflect it over a plane. So something I might consider doing is to kind of have two of these. And I'm going to show you why that might be useful real quick. So I'm going to actually, for now, hide this wing. And then I'm going to go up to this top bar, and I'm going to go to Contour and click that. Contour 1's fine. You can name these things more logically for your own sanity. I highly suggest doing that when you do your own presentation, but for this little demo, I'm not going to spend that time. So I'm going to display wall shear again, going to keep it local. Don't want it to display on the bottom. I want it defined on our wing. 11 planes is fine. I'm going to go ahead and apply that. That should be showing. Why is it not? I still had bottom selected. I want the wing. There we go. Now that the wing's being shown, what I'm going to actually do is go view, and I'm going to mirror this across the XY plane and click apply. So now what I have is kind of what my full wing design might look like, right? So now I have my wall shear on one side, and right now nothing is displayed on that other side. But if I go ahead and click my wing, it'll display it, and I can go back to double click my wing. Instead of smooth, move over to banded, 11. And you can see kind of what that contour plane would look like for both. So this should just be a reflection of each other. I believe they are. And that's one way for you to kind of maybe display your whole wing in case you find that desire. You might be wondering why they look ever so slightly different. That's because the wireframe is being displayed. So that's this big kind of box that we have. If I just click the check next to wireframe, that goes away, and they look more or less perfectly mirrored, with the only difference kind of being lighting effects. So that's one of the options that you can do with kind of some of these views. The other thing I found useful is instead of applying a mirror, I find translations can be quite effective when I'm trying to. So this is XYZ. I'm going to go into my Z axis, slip it into the flow by a meter. Let's apply that. Let's go 1.5 meters. Apply that. And you can see I've just kind of translated it off to the side. I'll do a full 2 meters and apply. So now I can kind of see them next to each other. The reason I might do this is I might want to show two different variables. So one of these might have my contour. I'm going to leave at wall shear, but I'm going to switch my wing over to, let's go with my pressure. So now I can see both my wall shear and my pressure. But you see, we only have one legend. I'm actually not a huge fan of how it's displaying the legend now, so I double-clicked on default legend 1. It's going to show variable and location, so the location is the wing, the variable is the pressure. I can have it vertical or horizontal. I prefer my horizontal legends myself. And instead of top left, I'm going to actually put this bottom left, not center, bottom left. So I click apply, and it moves down to that bottom left corner. I dislike scientific notation, so I'm going to move over to a fixed notation. We don't need 3 decimal points when it's a fixed notation. I only want 1. If I go apply, you can see now it's just 1 decimal point. And I think the text is a little big, so instead of a 2.4, I'm gonna just 0.2. That'll shrink down that text a little bit, and I don't want it interrupting this bottom bracket, so I'm gonna change the size down to, let's go 4. Let's see what that looks like. 4 is good. It can be a little longer, so instead of size, I'm gonna increase its aspect ratio to, let's say, 0.1. Oh, I went in the wrong direction. Let's go 0.05. That brings it a little thinner, and then I can move this maybe up to 5. And that kind of makes a small little legend out down the bottom. Now this is showing the pressure on my wing, but I also want to show this wall shear as well. So one of the options up here is a little legend option. If I click this, I can make a new legend. Click OK. I'll want it based on contour 1, perfect. Variable and location, great. I like my horizontal. This time I'm going to do top left. So we'll have 1 down here, 1 up here. Appearance, I believe, I did something like 5 and 5 if I remember correct. Move this down to 1, fixed. I think that was 5. And move this down to 2, 4. If I click apply, yes, perfect. Now we have our wall shear up top and my pressure down below. Something to keep in mind, because I used default as one of them, if I were to double click my contour, you can see this bottom one switches out to that contour instead of showing my wall shear. So whichever kind of geometry you're currently editing is what the default legend shows in its axes. So just keep that in mind. Easy to forget to change that. Some of the other useful features in this CFD post is defining certain locations. What I found really helpful in my own research is using this offset from surface feature. So I go to my user surface because I'm defining a pretty custom new surface. And instead of from a file, I'm going to go offset from a surface. So now I can make a wing, and let's offset it by, let's go 0.1. No, I'm going to go 0.01. So just a tiny little offset from it. Normal, uniform, that's all good. Going to apply that. It's going to take a little bit because it's doing a rather complex geometry here with kind of the bends in a wing. So we'll let that run. Hopefully it doesn't take terribly long. So now that it's finished running, that actually took quite a bit longer than I was expecting, but partially because I made a small little mistake. So if I zoom in here for you, I'm gonna uncheck my wing. Nope, I'm gonna uncheck my contour, so that's not in the background. You can see it actually generated our little surface on the inside of our wing. I wanted it the other direction, so I just need to slip in a negative here, and then I can apply it again. And then hopefully it doesn't take as long, and it should flip out to the outside. The reason it takes a little longer when it's going the incorrect way, the forward edge isn't too bad, but it's really the back edge that just makes it have to think longer. So just a heads up, if you see it taking a while, you can look if your direction is correct. Yes, so now we've moved that to the outside of the wing. And yeah, if I move to the trailing edge for y'all to see that, so that's a little bit of an offset surface. While I do love these offset surfaces, I love them because I can hide them and use them for other things. So I just unchecked that box real quick, and I'm gonna actually move over to my streamlines now and make some custom streamlines. So if I press OK, I can start my streamlines now from that defined surface. If I start them on the actual surface of my material, since we have a no slip condition, our velocity on the surface is 0, and that is no good for streamlines. They have nowhere to go, so that's why we need this little offset surface. I'm gonna move to like 50. You might want a denser cloud for when you do these. You have a couple different options here. Equally spaced does as it says, spaces them equally. I'm gonna show you a preview real quick. So all those little dots rather evenly spaced. That's a little hard to see with the coloring. So I'm gonna move this from variable back to constant, make it a white. Yeah, that'll be a little easier to see. Go back to my frick. Since I hadn't yet applied the streamlines, it disappeared. So you got to remake those, but that's pretty easy. Back to our user surface, gonna go like 50. That should be plenty for a demonstration. Maybe even 100. I clicked apply this time, so it's actually calculating those streamlines. It'll take just a little bit. So you can see the streamlines all generated on that surface. In this view, you can see where they all kind of started from. If I go preview points, those little green dots, they're a little small. They're quite small, actually, damn. But yeah, those little dots correspond to all my various streamlines that I'm making. And there's ones on the bottom, of course, too. And they're just Fluent off. You can also change these around, maybe a rectangular grid, gives you a little more control over how you do the spacing, but it'll still be kind of pretty well defined, pretty consistent, but can give you some of that control. You can also go vertex, which puts them at the vertex of cells. So if I move this up, let's go back to 100 and preview those points. You can see it's almost chaotic throughout it. This vertex method and face-centered method is going to bias places with more cells. So let's say you did extra refinement on the leading edge. If I were to do this vertex placement, it would put more points on my leading edge. Same with face-centered and free edge. So all three of these kind of bias it towards highly dense cell places, and those cells are defined in your mesh. But I found equally spaced to be the best working. We want it based on velocity for streamlines, though you could also do wall shear. Velocity is usually a better option though. And these are just forward, which kind of means forward in time. So you have the flow comes into the wing, hits it, wherever those points pick it up, it then sends it down. But what I'm gonna change it to is forward and backwards. Gonna apply those, and now what you should see is that the streamlines start climbing forward into the flow. So we'll get nice long streamlines extending all the way from kind of their origin through the wing itself, right? So now if I turn my wireframe back on, oh, that's the wrong one, wireframe, you can see they come from the inlet, come all the way, hit the wing where they had the points, and then shed it down into the downstream wake as well. There's nothing too fancy going on because this is just a standard wing. or a 0 degrees. So just a heads up on that. Nothing too fancy going on with this type. Couple options I want to point out on this one. First, this color option, again, you can move it down to local or whatnot, change it to a logarithmic, change the color map, right? I don't necessarily know exactly what arrow looks like, but you can see that map down on our legend below. So you have kind of a bunch of different options. You can go a zebra, which is just going to be, I believe, black and white for zebra. Yeah, black and white. But yeah, I generally find the default makes the most sense, except for kind of niche cases. And again, I suggest keeping this one smooth. The other big option for streamlines is you get this symbol option, and you can kind of show symbol, and that refers to these kind of, let's apply that. It should show, yep, all these little balls that are on it. And if I decrease the symbol size to 0.001, apply that, maybe just 0.1, my bad, or 0.01. Let's see, just 0.1, my bad. Yeah, there you go. You can kind of see them all starting in their kind of places. You have a max and min time. Let's set the interval to like 2. These balls are in reference to this kind of animate figure. So now if I animate this streamline and press play, you can see those balls come in and leave. And then if I stop, did I not stop? I did stop. You can kind of change those, loop, bounce, repeat, save, go down to options. This is the ball size. Again, you can change those to arrows or whatnot. So you have a couple options out on that. I generally avoid those, though. They're not usually too useful. The bigger thing we'd want to play with is what our line is. So you have 3 options: line, tube, and ribbon. So this line is, as implied, just a line. You only can change the line width, right? I can make it thin and kind of wispy, or I can make it very thick and fat, right? So those are rather thick lines, and they're pretty dark. I'll go back to 2 actually. One unfortunate thing about using lines is you can't use a line and transparency, so I'm going to make it 0.7, and you can see nothing changed. If you're displaying something on this surface, or you have a ton of streamlines and want to be able to kind of see into or through them, lines are not the way to go. You should use either a tube or a ribbon. If you use, I'll start with tubes. So you can see from that angle, they're very dark. Both tubes and ribbons don't usually work as well with lighting option enabled, so I usually turn that off, and that keeps them currently very bright, but we currently have quite large tubes, so I'm going to go back to my symbol. Instead of 1, I'm going to go down to 0.1. Let's see what those look like. Those look much better. So yeah, tubes are, as they imply, a tube. These guys, let's hopefully say I can see them from the back. Yeah, so these guys, you can see all what looks to be kind of little circles, but in reality they're octagons, right? Number of sides. If I change that to 4, you can see they all turn into squares. So you can use these, and they can be beneficial. You just might want to make them thinner and either increase or decrease the number of sides based on yours. These do work with our transparency, so if I go 1, they become completely invisible. If I go 0, they should be completely visible. And then if I go something like 0.75, right, you can kind of see that wing behind them, and they're pretty easy to see through. So depending on your application, you might want them transparent. Again, much more beneficial if you have a bunch of streamlines or if you have kind of some rotating flow. I like some transparency to see into the flow. I find it helpful. But the last symbol you have is this ribbon. Works a lot like the tube does, but as implied, it's just a flat surface. You can actually change the initial direction of the ribbon as well. So if I move this to a 1, that actually rotates all the ribbons. I don't know how well it'll actually be seen. We'll see if it does show up. But yeah, this can help rotate the ribbon. Usually isn't too impactful because, again, they're rather small in their current configuration. But let me give them a 1 scale. How does that look? That's actually quite hard to tell what's going on with 100. But yeah, this initial direction just is a factor to rotate the ribbon. Generally, you probably don't need it, especially for when you're having more streamlines, or if you're keeping your ribbon rather small. But if for whatever reason you have kind of 1 or 2 big ribbons, rotating it might be more beneficial for you. So, right, I just took off the rotation, and you can see it does change what you are seeing in your visualization. So keep that in mind as a kind of knob you can turn to play with your visualizations. Your limits, I'd suggest not playing with these too much. Basically, by changing my max segments, you can kind of start to cut off the end. So let's say I only wanted streamlines to end about here. I might decrease my max segments. It's very finicky, to be honest. And one of the things it does consider is the flow speed. So it won't necessarily directly cut the flow off here. It might have a weird looking pattern based on the speeds experienced at the wing, right? Maybe this stuff by the root slowed down just a tad more than the stuff by the tip. Sorry about that. And then if the root was slightly slower, it might have kind of a diagonal line at the back. So I'd stay away from playing with the limits, but you can explore that for your own knowledge. Render, same as before and same as view. You can kind of scale it, translate it, whatever you want. But that's more or less the basics of streamlines. Something I will say that I did already do is I made the wing just a white surface. If you don't have that, you can see through the wireframe. So the bottom streamlines get kind of, I confuse them with the top streamlines. So just keep that in mind as you play with different visualizations. It's often useful to leave the surface as solid. But yeah, that's kind of a rundown of streamlines for you. You also have particle tracks, which are I'm not going to go through them entirely. They're very similar to streamlines, just a tad different. They they're basically solved slightly different. That's the main thing with them. You can make a vector plane. I'll make a quick one for you, just so you can see it. I'm going to put it on my close wall here. Reduction factor, I like max number of points. Let's go 300 maybe? Let's see what that looks like. Yeah, that's not bad. So yeah, it just makes a bunch of kind of arrows in a plane. And of course, now my symbol option lets me change those arrows. So this is what's known as a line arrow here. You can see it's just kind of made out of a line. I can make it a 2D arrow, which fills things in. 3D arrow gives it some depth. Arrowhead only just makes it these little triangles. A crosshair makes it, as implied, crosshairs, which kind of weird for a vector, but might be better for some of the other variables that you could use, though I wouldn't suggest it. I'd kind of stick with your things that imply direction of kind of your arrows, 2D or 3D, depending on your application. But just, yeah, remember that lighting does affect how you view things. This was a good example, actually, of what vertex generation does, right? If I quickly slap my close wall and gonna go to my render and show my mesh, right? We have large mesh outside and very few arrows outside. We have tighter mesh in here and more arrows. And finally, very tight mesh right near my surface, which caused a lot of arrows to be generated right there. So that's a good example of what this kind of vertex sampling does. And then if I go back to my equally spaced, you can see relatively even distribution throughout. Or if I go rectangular grid, very uniform distribution throughout. And yeah, face center will cause pretty similar to what we see with vertex. So you can play with that option. It might be useful for your case, might not be. Anything else I want to show off? Yes, couple things. You can define your own plane as well. So I'm going to actually turn off my vector. Going to go ahead and define a plane. Okay. You can make it parallel to the X, Y, Y, Z, any plane you want. I'm going to change it in the YZ myself. Going to put it at, let's say, 2. And you can see I just made kind of this plane behind the wing. Generally, I don't love seeing these planes, right? Especially as a constant, they're rarely beneficial, but I'm going to show what they look like as a variable. My specific variable is actually going to be one of these derived variables, a vortex core, because I love my vortex cores. And let's go absolute helicity. I'm going to apply that. It'll take a little bit to load because it kind of, some of these derived ones, it doesn't expect you to use, so it kind of has to calculate what it is. And what do we see here? Right now it's using global. The surface of the wing has very high helicity compared to the rest of the flow. So I'm going to want to switch that down to local. And then we can see some of that helicity coming off the wing, right? So right behind the wing doesn't have too much, but the disturbed flow on the top and bottom does have some of this helicity. So yeah, that's one of the things when you define your own kind of planes, you can mess around with them. Again, I can make that smooth or banded if I wanted more of a contour type graph. So a couple options for you there. And then the final kind of visualization I'm going to show before I wrap this video up, I know it's quite long, sorry about that, is going to be how to do a volume render, specifically a volume render with a custom variable. So if I want to define a custom variable, I'm going to come out here to variable, click it. Variable 1 works perfectly fine. And you can make an expression here. I don't know exactly what functions you can use and can't use in this. Yeah, so you may want to look that up yourself, but I found that ABS standing for absolute value worked great. And then I'm going to go velocity dot curl x, close that brackets. Let's calculate global range. I'm going to click apply. So that calculated the global range of the absolute value of my velocity dot curl x. You might be wondering, hey, how did I know what velocity dot curl x is? You're given kind of all your variables up here. So, right, if I wanted to do something with wall adjacent temperature, I'd just write wall adjacent temperature. I got this velocity dot curl x. If I go to derived, then vortex core, then into my velocity curl, and here I have velocity.curl.x, and that's the variable I'm messing around with. I'm just using its absolute value. It goes both positive and negative. I just want to take the absolute value as an example for you guys. So making that, now that's called variable 1. Again, I suggest naming these something logical for yourselves if you're using them, but I'm just leaving them as defaults because it makes it easier for me in this little tutorial. So now that I have a custom variable I want, I'm going to make a volume render with it. So going to click volume render button. Again, that's just this guy up here. Going to click OK. Gonna click these three dots next to it. My user defined variable is down here. Click OK. I can keep the range global for now because I'm gonna play with it later, but I want to show it off to you. Resolution, I believe I want more resolution. Yeah, let's go like 50 planes. I hope that's enough. You just heard me say planes. How volume render works, it basically makes a series of planes that are semi-transparent based on the range you give it, right? So from my transparent to opaque, based on that range, it'll make 50 planes that have transparency. Color usually fine as default, though I will change it later. Smooth shading view, I'm going to leave that all as defaults for now and just apply. So usually this takes some of the longest when you make it great. I did relatively few planes for this one, so it shouldn't take terribly long, but yeah, just heads up, this can take quite a while. Okay, and what you just saw come up is my volume render, and you might be thinking, hey, Andrew, nothing showed up. You're correct, nothing did show up, and that's because my range is too high. So there's probably 1 or 2 points right near the wing surface that have incredibly high curls, and that's why we don't see anything. So I'm going to go, instead of global, I'm going to go user specified. And I'm going to take 0 to, let's go, maybe like, let's try 10,000. Let's just try 1,000 and see what that gives me. I've seen enough of these to kind of know what numbers to play with, but if you're new to this program or this visualization style or this variable, you're going to have to play around a little more to see what's working. So now you see just some wisps coming up. So that means I'm still too high, so I'm just going to go to 100 and see what happens. Letting it calculate that new one. And once that gets going, we'll hopefully see something rather neat. Yeah, we're starting to get there. Still a bit high. I'm seeing some greens, some reds, some blues. I'm going to go down to 50 actually. Let's try that. Again, 0 degrees angle of attack isn't the best for this visualization that I chose. Usually better at some higher angles, but we're kind of stuck with what I have already done. You can also see in this visualization those planes I was talking about. Right, so it has 50 of these planes going all the way down. We can't see all of them because some are beyond that wing and not having any kind of curl happen to them. As I rotate around, it might switch. Yeah, there we go. You can see the line orientation switched. So if I'm kind of looking at the back, it'll only kind of display in a way that makes sense for what my needs are. So as I look down the back of this, it has the planes oriented in a different direction than if I'm looking in the side, and you can see that flip happen depending on my angle. Gonna go a little lower. This was quite a bad one, sorry. That was on me for choosing this. So going down to 25, hopefully seeing some interesting behavior out a little more in the wake. You can start to see what's known as a tip vortex, with the tip kind of having more of it. But again, that was my fault for choosing this variable at 0 degrees. Just doesn't show too well, but it should work for my purpose. And one of the main things I want to show you is that I can have a different variable than what my volume render is generated on. And instead of using my custom defined variable, which is the absolute value of my vortex core, I'm going to actually go to my velocity curl x straight up. And still going to do a user specified. 0 to 25, I can now have negative numbers because I'm no longer doing an absolute value, and I'm going to go with -10. So let's see what that looks like. Perfect. That's exactly what I'm hoping to see. I'm going to actually move it out to -25. Yeah, that looks pretty good. So as you can see, the top of my wing is generating kind of positive curl, and the bottom of my wing generates negative curl. So by having kind of this custom variable, I'm able to display my curl, and then by changing my color, I'm able to display both positives and negatives. You might be wondering right now why I didn't use just velocity curl to begin with, and I very well could, and I'll show you what that might look like. So if I used velocity curl x to start with, still going to use my 0 to 25 bounds. If I apply that, what you'll see is that all my bottom surface is going to disappear. I'm going to have no blues show. So giving it a little time to calculate that. So yes, all that blue on the bottom just disappeared because it is completely transparent. So any number lower than 0 is going to be completely transparent, and any number higher than 25 will be as opaque as it gets. And I can define how opaque it is based on this 0 to 2 or 0 to 1 scale. So if it's 0, it's completely opaque. You can't see through it at all. If it's 1, it's completely transparent and will not show up. But by making it transparent here, it won't show. Now you might be saying, well, of course it's not showing. -25 is less than 0. Why don't you make this -25? And I can try that, but we should see an error pop up. Or at least I have in previous versions of the software. I might look like an idiot here if it rolls out. No problem. Yes, here's the error I'm expecting to see. My entire domain just got shown, and that's because 0 is not set as transparent, and everything away from the wing has 0 curl, right? Curl is introduced through our wing surface, and since 0 isn't what we define as transparent, all that region shows, which means I basically see nothing. So that's why it was very valuable to define our own custom variable as just the positives as that absolute, so that we don't run into 0 not being transparent. So yeah, I think that's more or less a overview of all the programs that I used, or how to use Workbench in general. So I'm going to go ahead and close this. And that should save. Yep, you can see that check mark. And the final thing to wrap it up is I'm going to rename this to AOA 0. And then I'm going to right click on Fluid Flow and I'm going to duplicate it. Now what you'll see is after a little bit, it'll make this entire cell block a second time called either copy AOA 0 or AOA 0 copy of AOA 0. I'm going to rename this to AOA 2. Angle of attack is what AOA stands for. Going to go into my geometry tab. And then I'm going to go to this rotate. I'm going to rotate it by 2 degrees. Enter and generate. You should be able to see just a slight angle on that guy. So now I'm good to close this. And now you'll see kind of this circle arrow come up, and that just means it needs to reread what's above it for all of these. This is the check with the arrow up means basically everything's defined and it needs to reread what's above it. The circle the circle arrows means it needs to reread, and then based on rereading it will redefine some of the things it needs to. But what's convenient about this is I can actually just hit update project and it's going to go through, update my geometry, update my mesh, update my setup, and then start running the solution and then spit out my results. These results will have the same display options that I just defined before as I was going through my angle of attack, my 0 angle of attack. So yes, that's kind of the big advantage of using Workbench. Quite a long process to get your first iteration, first angle in this case, running, but it makes it very convenient for my subsequent angles where I just have to duplicate these a bunch, change that one factor in my geometry, click update, and it'll run through all my different variables. So again, I hope this helps whoever's out there looking to use Workbench and Fluent in general to run their programs. So yeah, that's the end of this video. Sorry if it was a bit rambly. Yeah.